Hi everyone! The effect we'll be creating in this video is something I had been planning for a long time and now I finally implemented it. As the title suggests, it will be a simulation of raindrops falling onto a water surface, including the typical expanding ripple circles. Let's get started. Okay, let's start. This time it's not about any transition between scenes, so we can get by with a single background image. I'll create the usual scene with a Sprite 2D node and then apply a new shader material to its material property. So right-clicking the scenes folder, create new scene, and it's 2D scene, this is correct. And let's call it raindrops. Okay, why not? Very well. And I will drag the usual image found in JPEG, which is the screenshot from our game Whispers of Prague. And Godot automatically created a Sprite 2D node in the inspector. And let's do the usual stuff in the scene panel. And let's do the usual stuff in the inspector. Expanding offset and cancelling centered. And expanding transform and resetting position to 0, 0. So here it is. And let's scroll down to the materials section where I create a new shader material, click it and add a new shader, which is type shader mode canvas item. The name is raindrops.gd shader and the path I will put it to the usual shaders folder. Clicking create and click again to open it in the shader editor. Okay, and as always, we'll just expand this a little bit. And as usual, we'll improve the readability of the shader code by deleting everything that won't be needed. That way, only the fragment function will remain. So I'm deleting vertex and deleting the commented out light. Ctrl S to save. Okay, so this isn't the first displacement effect I've created on this channel, but it still differs from the others in various details. We'll control these details using uniform parameters, of course, and 8 of them this time. So we make the effect of falling raindrops as realistic as possible. So let's start with the simplest one, a parameter that determines the number of simultaneously active drops. Let's add it right here, uniform float drop count with a hint range, and let's put the initial value, let's set it to 16, okay, and the range would go from 1 to let's say 128. Yeah, I like powers of 2, and the step is of course 1. Okay, next it will be useful to set the speed at which the circular waves propagate. The second parameter, uniform float ripple speed with another hint range and the initial speed 0.4, and the speed goes from 0 to, for instance, 2, and the step point 0.1. Very well. We'll also need a maximum radius for these circles. So once it's exceeded, the effect will disappear. The third parameter, uniform float ripple max radius, and again our hint range and the initial value would be, I think I said 0.35. Yeah, this should be it. And from 0.01 to 1 with the step 0.01. Okay, and every displacement should have an adjustable distortion strength, which we'll control with another parameter, uniform float ripple strength. Okay, hint range, and starts at 0.1, and it goes from 0 to 1 with the step 0.01. Alright, a raindrop usually doesn't create just a single ring but a sequence of several concentric waves, so we'll define their count with this parameter, uniform float. Ring count, a hint range, and let's start with 3 rings, and the range goes from 1 to, let's say, 10. Okay, and again the step is 1. Alright, the next parameter will determine how quickly the waves fade out at their outer edge. Uniform float fade power, hint range, and 2 would be the best default value, and it goes from 0.1 to 5 with a step 0.01. Okay, and finally we'll add parameters to improve the visual appearance of the waves. The first, set the color, which will be quite transparent by default so the waves don't distract too much from the image. Uniform vec4 RGBA format, ripple color, and the hint is this time source color, and the vec4, the initial value I think 55.78.1, and let's make it quite transparent, 0.18. Okay, and of course source color means that we will get the color picker in the inspector. Alright, and the last parameter controls brightness, simulating reflections on the rippling water surface. Uniform float, shimmer, intensity, hint range, and let's make it average 0.5, and it goes from 0 to 1 with the step 0.01. Okay, so with the parameters done, I'll now add the usual function for generating pseudorandom numbers. This will give us a reasonably uniform distribution of falling drops. Okay, and let's expand this window and paste the function right here. It is the usual function I used in previous tutorials many times. It's called hash12, meaning that the return value is one-dimensional float and the input parameter is two-dimensional vector. Okay, next we'll move on to the fragment function, where I'll write the base code and prepare for calculating individual waves, which we'll later implement in a separate function. So first, I will prepare the aspect ratio adjustment. We won't use it right now, but later when we get to preparing the waves and we want them to be circular rather than elliptical, regardless of the image dimensions. So vec2 UV is simply UV, and now the resolution vec2 resolution is 1 divided by texture pixel size. Okay, then I'll define the usual time variable using the internal time and the ripple speed parameter. Float time equals time times ripple speed. Okay, now we need 2 accumulators to build the final effect. One will handle displacement and the other the color tint. So vec2 total disp for displacement is simply the 0 vector, and the second one float total shimmer starts at 0. Then we need to compute the contribution of each drop and add the results to these accumulators. So I'll create a loop to handle that. For float I starts at 0 and I is less than drop count I++, and inside I will write a few lines, then explain them. vec2d float s evil drop IUV resolution time D and S and accumulators total disp is increased by D and total shimmer is increased by S. Okay, so inside the loop, we call the eval drop function, which we still need to implement. Notice that the last two parameters, D and S, don't have assigned values. We just declare them right here. That's because they will be filled inside the eval drop function and then used here in the fragment function to be added to the accumulators. Okay, so they will have the out parameter indicating their output only parameters. So out modifier, sorry. So let's write the beginning of that function just before the fragment function. So void eval drop, and now the parameters float ID of the current raindrop, vec2 UV, the coordinates of the current pixel, vec2 resolution for the aspect ratio recalculation, float time for the animation, and now out vec2 disp displacement and out float shimmer. All right, so now the code is compilable again, and of course we need to initialize these output variables with this. This is simply a 0 vector, and shimmer, let's start at 0. Okay, now I can return to the fragment function and finish it. So right after the loop, let's continue. First, we retrieve the pixel color at the position deformed by the previous calculation. And since this might go outside the image bounds, we clamp the results to the 0 to 1 range. So vec2, let's call it sample UV, is, as I said, clamping to the range and UV plus total disp. Okay, and now the clamping bounds vec2 0 0 and vec2 1 1. Okay, and now we need the pixel at the coordinate. So vec4 base, let's call it base, is the result of the texture function applied on our texture and sample UV coordinates. Great. Next, we'll add the reflections, again clamping the values to avoid color distortion. So float, let's call it shimmer clamped, and it equals clamp, of course, of total shimmer, and the range is 0 and 1. This time there are no vectors, just float values. Okay, and no, negative 1 and 1. This is different because the shimmer will change the color in both directions, so it can go to some negative numbers as well. All right, and let's define the color of this highlight. Let's call it a highlight. Vec3 highlight is simply ripple color parameter and RGB components for vector 3 multiplied by ripple color alpha value and multiplied by the shimmer clamped value. And since it can be a negative number, let's make sure it is clamped to 0 in this case. So shimmer clamped and max of shimmer clamped and 0. Okay, and finally we output the combined result. Color, the output value is vector 4 of base RGB plus our highlight vector and base A for the alpha value. Okay, at this point, if we return the image, we don't see any changes, of course, because the eval drop function doesn't do anything. We can take a look, it's empty. Almost. But these preparations were necessary, so we can now move on to the actual implementation of the effect and observe the results step by step. Okay, so I'm back at the eval drop function, and we have the first parameter called ID of the type float. It's the ID of the current drop, which we'll use to determine the pseudorandom position and other properties. For this purpose, I'll define a variable called seed, which will serve as the basis for these pseudorandom calculations. The numbers I will use in this formula are completely arbitrary. So vec2 seed equals vec2 and now ID times 0.37 plus 1.3 and the second part ID times 0.71 plus, for instance, 0.9. Okay, next we want the drops to avoid looking synchronized, so each one will have its own wave period, something between, let's say, 2.2 and 5.5 seconds, like this. Float period equals, and let's make a mix of, as I said, 2.2 and 5.5, and something between that, again based on the hash12 function applied on the seed vector plus, and let's give it some small shift, so vec2 0.1 and 0. Okay, so to further enhance the sense of randomness, we'll also add a pseudorandom start offset of the animation, so float, let's call it phase. Phase is again hash12 and this time seed plus vec2, 0 and 0.3, and multiplied everything by the period value. Okay, now I'll use these variables to define the variable called age, which is normalized to 0 to 1 range and represents the current phase of the effect. Float age is fract of time plus phase divided by period. Okay, at this phase, it would be useful to work with a single drop first and expand the functionality later. So for now, I'll temporarily set its position to the center of the screen, hard-coded. Vec2 center is simply vec2.5. Okay, and to make sure I don't forget, I'll also reduce the drop count parameter to 1 in the inspector. Let's expatiate the parameters and drop count setting to 1. Next, we need to determine the distance of the current pixel from this center. I'll create a vector called delta, adjust it for the aspect ratio using the resolution parameter and compute the distance. So vec2 delta is simply UV minus center. Now the aspect ratio recalculation. Delta x is multiplied by resolution x divided by resolution y. And finally float this for distance is simply the length of this delta vector. Okay, in addition, we need the direction, which is the normalized delta vector. In case the current distance is too small, let's add a safeguard to ensure the direction is never 0. So it will be this kind of formula. Vec2 dir is, and now the ternary operation. So if this is greater than some small number, 0001, then we simply normalize it. Otherwise, let's use this simple vector 1 and 0. This probably won't be necessary, but let's use it just to demonstrate how such a safeguard can work. Okay, so far we've been defining helper variables that are necessary for the next steps, but we are getting close to the first visible result. Next comes the life variable, which defines gradual decay. Float life is 1 minus small step of 0.6 and 1 and age as the weight value. All right, now I'll add a variable called contribution, which in its final form will include the actual wave calculation, but for now will simply be equal to wave float. Okay, it simply contains the value which contributes to the total displacement of the image using all the waves we generate. Then we can define the output variable disp, so this parameter, and using the direction, the contribution, and the ripple strength parameter like this. Disp equals dir times contribution times ripple strength. Okay, and now something starts to happen. It's not the expected result yet, of course, but we can build on this for further calculations. We still need to fill the output variable shimmer as well. So shimmer equals, again, contribution times shimmer intensity parameter. Okay, so to get expanding circles instead of this strange distortion, we need to know their radius. I'll add that right after defining the age variable, which should be right here. Okay, since it directly depends on that. So float radius equals age times ripple max radius, another of our uniform parameters. Now, let's get back to the definition of the contribution variable, which is right here. Before that, we'll define the wave using this radius and the sine function to create concentric circles. So before this line, I'll do this float wave argument equals, and now a little longer formula, dist divided by max of radius and 0.0001, again just to make sure that we don't go somewhere we don't want to, minus 1 multiplied by ring count and multiplied by tau twice pi, because we'll be working with the trigonometric function and we want to respect the period, which is usually pi or twice pi. All right, and float, let's define the wave. So wave is simply sine of our wave argument. Okay, and now when we add this wave variable to the contribution calculation, we get a slightly better result. So instead of life, it will be wave times life. Wait for it. Okay, something is definitely going on there, and it looks much more like the expected ripples. However, it looks like the waves are spreading infinitely, so we'll climb them using a simple mask with the step function. So just before the contribution again, let's define float mask is, as I said, a step function applied on the dist value and radius plus ripple max radius, and I think it's too big, so divided by 2, multiplied by 0.1, and let's include this mask variable in the contribution as well. So wave times life will change to wave times mask times life. Okay, and it seems to be even better than before. This gives us another improvement, but we are still missing the intensity fall off with the increasing distance from the center. So I'll define a variable called env, which is short for envelope, based on an exponential with a negative argument, meaning it gradually approaches 0. Again, we need to be careful not to work with negative arguments, so we'll make use of the max function. So let's do it just before the mask definition right here. Float env equals exponential of negative pow of max of dist minus radius times 0.15 and 0 divided by bracket ripple max radius times 0.18 times I said 0.18. Okay, close bracket, and the second argument is fade power. Okay, is it correct? Let's add a semicolon and it should be compilable. Yeah, this is right. So again, we have some arbitrary numbers here, the result of previous experiments. And this is just the first part because we'll be multiplying this formula by another exp to give it even better shape. So multiplied by x of, again, negative power of max radius minus dist and 0 divided by ripple max radius times 0.25 and bracket, comma, and to the power of fade power. Okay, and this should be it. Of course, this looks pretty complicated, and if you don't want to risk making any typos, just use the version from the Godot shader pack, which is definitely correct. Okay, and that brings us to the final refinement of the contribution variable. And let's add this env to the multiplication. So it would be wave times env times mask times live. Okay, and I think now it looks definitely as we want to. Perfect. All right, so I guess it's time to implement a pseudo-random distribution of drops across the entire surface. So I'll rewrite the definition of the center vector using the #12 function. Okay, let's find it. I think it's somewhere here at the start of evil drop, the here center. As we can see, it's hard-coded to vector 2.5, and now let's change it. So it would be vector 2, but we'll use the #12 function several times. Seed plus vec2, and for instance, 0.2 and 0 to give it some offset. And the second argument, I think I will just separate it to 2 lines to make it better readable. Okay, and hash h is missing, sorry, and here 2, and let's change the vector to 0.20 and 0.2. Very well, and now we can see that the drop is situated elsewhere, not in the center. And let's add a slight offset so the drops don't always fall in exactly the same spot. And finally, we'll clamp them a bit away from the edges of the image. So right after the definition of center, let's increase the center by a small amount, 0.04 times vec2, and now I will do this sine, so it's variables over time times 0.13 plus seed.x times tau, again the period twice pi, and the second argument would be cosine of time times 0.17, again arbitrary numbers, plus seed dot y times tau. Okay, and I think the semicolon is missing right here. And as I said, clamping, so center equals clamp of center and vec2 0.05 and vec2 0.95. So it's never sorry, once again, vector 0.95, so it's never exactly at the edge of the image. Okay, and now when I restore the original value of the drop count, let's click it, we can see the drops and their waves behaving as expected. Let's show the whole picture. Okay, and I think we are done. We can now try different parameter settings and admire the results. So for example, if I increase to 128, it is really dense right here. Let's increase the speed. Now it's like a very fast rain, or 0 means completely stopped. We can increase the max radius. Now it's much bigger or smaller. And we can also change the ripple strength. So now it's more distorted than before. So let's just get back to the original values, or maybe, yeah, let's increase the ring count. Now it's denser in the terms of the rings, or just one ring. Okay, not bad. The fade power changes how the rings probably fade at the edges. Yeah, now they are active a bit longer. Or we can, let's just increase the number so we can see the result better. We can change the ripple color. So for example, if I increase the alpha value, now it's much more prominent because it is no longer almost transparent. So let's get back. And of course, we can change the shade as well. And the shimmer intensity, yeah, probably if I keep the less transparent volume or opaque, we can observe the shimmer intensity more than that. Yeah, this is it. Perfect. And that's everything. Thank you very much for watching. I hope writing a slightly longer piece of code wasn't too much trouble, because the result is definitely worth it. And of course, if there were any typos while writing the code, you can use the finished version from the Godot shader pack, which I link in the video description as usual. For now, take care, good luck with your projects, and I'll see you in the next video.